Alright, stop what you're doing, cause I'm about to ruin image and the style that you used to. I look funny, but yo, I'm making money, see? So yo, world, I hope you're ready for me. Now gather round. I'm a little fool in town, and my sound's laid down by the underground. I'm drinking about the Hennessy you got on your shelf. So just let me introduce myself. My name is Humpty, pronounced with the Humpty. Yo, ladies, oh, how I like to be. And all the rappers in the top 10, please allow me to bump me. I'm stepping tall, y'all, and just like Humpty Dumpty, you're gonna fall when the stereos pump me. I like to rhyme, I like to be funky, I'm spunky, I like my oatmeal lumpy, I'm sick with this, straight gangster Mac. But sometimes I get ridiculous. I'll eat up all your crackers and your licorice. Hey, yo, fat girl, come here. Are you ticklish? Yeah, I thought you're fat. Look at me, I'm skinny. It never stopped me from getting busy. I'm a freak. I like the girls with the boom. I once got busy in a bathroom. I'm crazy. Allow me to amaze me. They say I'm ugly, but it just don't faze me. I'm still getting in the beats, and I even got my own dance. It's your chance to do. Come on, do the Humpty Hump. Come on and do the Humpty Hump. Check me out, y'all. Do the Humpty Hump. Just watch me do the Humpty Hump. Yeah, do you know what I'm doing? Doing the Humpty Hump. Come on, do the Humpty Hump. Do the Humpty Hump. People say you're Humpty, you're really funny looking. That's alright, cause I get things cooking. You're scared, you're glad, you're constantly trying to compare me, but you can't get near me. I'm giving more C, and on the floor B, all the girls, they adore me. Oh yes, ladies, I'm really being sincere, cause I'm a Humpty nose will tickle you. My nose is big. I'm not ashamed, big like a pickle. I'm still getting paid. I get by the ladies, you know I'm in charge. Both I'm living and my nose is large. I get stupid. I shoot an arrow like Cupid. I use a word that don't mean nothing, like Luke did. I sang off the what you like, and if you missed it, I'm the one who said just grab them in the biscuits. Also told you that I like to bite. Well, yeah, I guess it's obvious. I also like to write. All you have to do is give Humpty a chance, and now I'm gonna do my dance. Humpty dance, it's a chance to do the hump. Come on. Yeah, sexy baby. Do the hump, come on. I'll do the Humpty Hump. Sexy baby. Everybody, come on and do the Humpty Hump. I'll do you know with the Humpty Hump, y'all. I'll do the Humpty Hump. Watch me do the Humpty Hump. Yeah, that's a break, y'all. Look at that bass groove right here. Yeah. Now I told y'all a little bit about myself. Let me tell you a little bit about this dance. It's real easy to do. Check it out. First I lift to the side like my legs working, shaking and twitching, kinda like I was smoking. Crazy, whack, funky. People say you look like MC Hammer on crack, Humpty. That's alright, cause my body's in motion. It's supposed to look like a fit or a commotion. Anyone can play this game. This is my dance show, Humpty Hump's my name. No two people will do it the same, you got it down. When you appear to be in pain, humping, funkin', jumping, dig around, shaking your rump, and when the doodle jump point points a finger like the sun, tell them step off, I'm doing the hump. The Humpty dance is your chance to do the hump. Everybody, do the Humpty Hump. Come on, do the Humpty Hump. Say it, baby. Do the Humpty Hump. Do the Humpty Hump. Watch me do the Humpty Hump. Do the Humpty Hump. Black people. Do the Humpty Hump. Do the Humpty Hump. Come on, white people. Do the Humpty Hump. Do the Humpty Hump. Puerto Ricans. Do the Humpty Hump. Do the Hump. Samoans. Do the Humpty Hump. Do the Humpty Hump. Yeah. Let's get stupid. Do the Humpty Hump. Do the Humpty Hump. Do the Humpty Hump.
Exactly this, Shian. Any finite polynomial is its own power series. Absolutely. Power series, well, power series with center 0. But then if you take any other center And we'll do an example momentarily where we'll see that that is equivalent to essentially dividing by x minus c. All right, now, I don't know when the Math 141 grades are coming out. I asked the markers to mark them ASAP, but, they had final exams themselves, so, I like to give them a break. And Taha is asking an excellent question. Can we represent sine x as an infinite polynomial as a power series, right? This was one of the questions that arose naturally. We're going to see that today. But before we do so, let's do one or two more examples of stuff we were doing last time. So from page 793, we were asking the question, can we represent this function as a power series? So can we represent this function as a power series? Well, as we did with the tangent, or the arctan rather, we started by looking at the derivative. I think it would be a good idea to do that too. So Jamie's book ends at chapter 11. That's because you have the short version, which was for Cal 1 and Cal 2. You have two options. There's a complete book, which covers all the previous material and what we're going to do now. Or you can buy the multivariable version, which has chapters 11 onwards. Or, of course, there are the free online resources that I've given links to as well. So let's look at the derivative here. The derivative is, of course, 4x cubed over 1 plus x to the 4. Well, by the way, this morning's song was brought to you by Digital Underground. Shock G passed away last week in relative obscurity, I thought, so I figured we would pay tribute this morning. All right. Indeed. So if we're looking at this, and if you remove the 4x cubed, you're thinking to yourself, kind of looks like a geometric series there. And that's exactly what we're going to do. Right, so 1 over 1 plus x to the 4, very similar to the derivative of arctan that we manipulated. We're going to do the same thing here. This is 1 over 1 minus negative x to the 4. And now you see the geometric feel to it. Right, this is the sum from 0 to infinity of negative x to the 4 to the n, or if you prefer, negative 1 to the n, x to the 4n. So if we transport this over here, this is going to be just 4x cubed times this business. And if we bring that in, and there you have it. So this, here we have a power series representation for the derivative. And you know that this is valid if this thing is less than 1 in absolute value, right? So you know that this is valid for x less than 1 in absolute value. Brune is asking why we work with the derivative to find the power series, because it's easier. It's easier. When you take the derivative, you recognize that you have some sort of geometric series happening here. And we know the power series for the, well, I mean, we know the 1 over 1 minus a business. So that's an excellent starting point. And this is going to be important later on, because as, I forget who was asking about the sine business, we're going to see a nice systematic way to get power series representations for essentially any function. And well, I mean, Taha is, so it was Taha with the sine business, and now coming back with, can any function be reconstructed as a power series, or does its derivative have to be convenient? The derivative doesn't have to be some sort of geometric series. However, the function has to be infinitely differentiable. And Taylor series is what I'm hinting at. Absolutely, we're going to see that momentarily. Well, so now this does not represent the original function, but rather the derivative. But now we're going to integrate, as Aisha suggests, or it may be Aisha. I may be mispronouncing that. Sorry about that. Why is this only for absolute value of x less than 1? Well, here it was actually for negative x to the 4 and absolute value less than 1, right? Because it's a geometric series result that we're working with, which is equivalent to this. How are we able to get the 4x cubed in? Well, we're treating this as 4x cubed times 1 over 1 plus x to the 4. So we have the derivative as this, and consequently the original function, you know from the theorem we had yesterday that we can integrate term by term in the interval of convergence. So if you integrate term by term, the only thing that depends on x is this. Well, right now the answer is only valid for x between negative 1 and 1, correct? But when you integrate, you know that the radius of convergence is at least as large. So we know that the answer is going to be at least valid for negative 1 to 1. Could be further, could be larger, but it's going to be at least for the interval negative 1 to 1. And if you integrate term by term, what do you get? Antiderivative of x to the 4n plus 3 is x to the 4n plus 4 over 4n plus 4. The 4's canceled out, and we have a constant of integration. What does it mean to integrate term by term? You just integrate, right? Because, I mean, what is this? This is, when n is 0, this is 4x cubed. When n is 1, this is minus 4x to the 7. And then we get a 4x to the 11. And so on and so on. So we're just integrating each of these terms one by one. That's what integrate term by term means. Right, so when you integrate this, you get x to the 4 minus 1/2 x to the 8, and so on, which is exactly what this is going to be. Right, convince yourselves. When n is 1, this is 4/4, so this is x to the 4, which is exactly the antiderivative of this. And then when n is 1, here we have a 2, so 1/2 x to the 8, exactly as expected, and so on and so on. So we're saying that this function has power series representation. The 4's cancel out, right? You see that? -1 to the n, x to the 4 times n plus 1 over n plus 1, or plus an arbitrary constant. I keep forgetting it, but it's there. And maybe you want to clean that up, right, by making a shift. Maybe you don't. It's not. It certainly looks better. You're integrating over x, absolutely. Absolutely, because the derivative, I mean, I've rubbed it off now, but the derivative was in terms of x. And I mean, we didn't, it certainly makes it look better. Is shifting necessary? In some cases it is, but here it certainly makes everything look good. Yeah. Let's get into the habit of actually changing it to make it look as pretty as possible. I mean, I've rubbed off the interval of convergence, but we haven't worked it out yet, but we know the interval of convergence is at least -1 to 1, at the very least. So 0 is in the interval of convergence. And what is this? I mean, we already have it here. This is that. So when x is 0, you see that the whole thing is 0. So at x equals 0, which you know to be in the interval of convergence, right? Because our interval of convergence is at least -1 to 1. So when x is 0, here we get ln 1. This whole thing is 0 plus the arbitrary constant. So you see that c has to be 0. In other words, ln of 1 plus x to the 4 is equal to this business. And this is valid for x between -1 and 1, at least. Since we are integrating and could be differentiating the power series. Does that mean we are dealing with an open interval of convergence? It does not. The interval of convergence could include some endpoints, and let's calculate it here. Let's work out the interval of convergence. What is the interval of convergence here? Why is it valid for at least -1 to 1? Because originally our geometric series is valid for -1 to 1. So we made use of that. And then we multiplied by 4x cubed, which is a polynomial, so that converges everywhere. And consequently, the intersection of the two, the smaller set for which both converge, is -1 to 1. And when you integrate, we had this theorem yesterday, that when you integrate, the radius of convergence is at least as large as what it used to be. So we had a radius of convergence of 1. So this will converge for at least -1 to 1. But let's work it out just for fun, just to see what it really is. And we're going to apply the ratio test. Right? Because of the absolute values, these don't matter. X to the 4n and x to the 4n plus 4, these cancel out. And we are left with x to the 4 n over n plus 1. And as n goes to infinity, it's easy to see that this goes to 1. So this limit, well, let's take an extra step in case you don't see it. By factoring out, the n's cancel out. This goes to 1, so this whole limit is x to the 4. And what do we need for convergence? For convergence, we need x to the 4 less than 1, which is equivalent to x being between -1 and 1. So for the product, the interval of convergence is the intersection of the intervals of convergence. Here we check for absolute convergence. That's absolutely right. So in this interval, your power series converges absolutely. And now let's check the endpoints. If x is -1, what are we looking at? -1 to the n minus 1, -1 to the 4n over n. And this is always even, so this is always +1. So this is the set, the series, -1 to the n minus 1 over n. I'm quite certain we saw that yesterday. Harry's asking why we set x to the 4 Less than 1, well, we did the ratio test. And for convergence, we need the limit to be less than 1. Exactly as Nicholas suggests. So we have this. Again, I'm quite certain we saw that yesterday. But let's do it. If you take absolute value of this, you get the series 1 over n, which you know to be a divergent p-series. P is equal to 1, less than or equal to 1. So the series does not converge absolutely, but it is alternating. The limit of 1 over n is 0. And if f is 1 over x, then the derivative is minus 1 over x squared, which is less than 0. So the series, negative 1 to the n minus 1 over n, converges conditionally by the alternating series test. And similarly, if x is positive 1, we have the series we have the exact same series. So you know that that converges conditionally by the alternating series test. So this is conditionally convergent. And consequently, the interval of convergence includes both endpoints. When in the geometric series business, it did not include the endpoints. Why are we checking absolute convergence when in the book they only check normal convergence? We're smarter than the book. We know that if you have a series with both positive and negative terms, two questions arise naturally. Does it absolutely converge? And if not, does it conditionally converge? Here we're just giving as much information as we can. This series conditionally converges. And of course, you realize that the radius of convergence is 1. Follow-up question. We have just shown right? This is 1 minus 1/2 plus 1/3 minus 1/4 plus 1 over 5. We have just shown that this, so we always need to check for absolute convergence? Absolutely, yes. Nicholas says that in the book, they state when you differentiate or integrate, the radius of convergence is always the same. Whereas I said the radius of convergence is at least as large. who's right? Well, the theorem I gave you was a bit more inclusive than the theorem they give in the book. In the book, they have a separate theorem for differentiation and integration, whereas I grouped adding, multiplying, dividing into the same theorem. But let's think about that for a moment. Our theorem says the radius of convergence is at least as large when you differentiate and when you integrate. But if it's at least as large when you differentiate, and then when you reintegrate, it's at least as large as the derivative, then of course they have to be the same. Right? So that theorem I gave you was more general, but it implies that when you differentiate or integrate, they're actually the same. It's all good. So, but it's a very nice observation, and an important one as well. Let me bring your attention back to this. We have just proven that this conditionally converges. What does it converge to? Why do we always have to look at absolute convergence? Because it's more, it's a stronger form of convergence. As you know, if a series absolutely converges, then the series converges as well. So Nicholas is asking, what about addition and subtraction? Doesn't that mean addition and subtraction always keep the same radius as well? No. It's tempting. However, the problem is, because you're thinking to yourself, differentiation versus integration, these are inverse operations, so you're canceling them out. Addition and subtraction are also inverse operations, so you're canceling them out. Shouldn't you be able to get back what you started out with? And that's the problem, right? If you differentiate and then you integrate, you essentially get back what you started out with. If you subtract and then you add, you don't necessarily. What do I mean by that? What do I mean by that? Take two of these, right? Take two of these and subtract them. Here, this converges in this interval. So when you subtract them, this minus itself is 0. And the interval of convergence for 0 is the whole real line. I'm pointing to this for convergence in here. That's not what I should be pointing at. I should be pointing at that. So take two of these and subtract them. Is conditional convergence different than regular convergence? Well, what does regular convergence mean? We don't really use that term. I suspect you mean just looking at the series itself. Does the series converge? And versus the series of absolute values. That's essentially what's going on here. Right, so we have established convergence. Well, in this case, subtracting actually increases the interval of convergence. Indeed. But in many cases, it stays the same. So that's why we say the radius is at least as large. We established convergence of this series. What does it converge to? But it can never decrease. Exactly, Grisha. That's the theorem we had yesterday. The radius of convergence is at least as large. Ln 2, thank you. Ln 2 indeed. Ln 2, right? Because we have this. We have this equality, and this is equal for any value of x in the interval -1 to 1. So when x is 1, or when x is -1, you get this series, and it's equal to ln 2. So now we have a nice way to evaluate what series actually converge to. If we can represent a function as a power series, Hugo is asking, if we subtract, we get a radius that is bigger, then addition with the same number still does not move. No, but you see, I'm saying, so suppose you have some power series. Let's call it P of x, right? So you have this power series. And that power series converges in the interval -1 to 1. So the radius is 1. And now let's subtract the 2. So we have 0. 0 is its own power series. And that converges for all values of x. So you see that the difference, right? This converge in the interval -1 to 1. So did this. But when you subtract the 2, you get convergence on the whole real line. Questions? Oh, I see what you mean now. I hadn't understood where you were going with this. So now you're saying this converges on the whole real line. This converges on -1 to 1. So their sum. So this converges on R. This converges on -1 to 1. So that's what we were saying originally. The sum is going to converge on the intersection, right? I mean, you have to be comparing apples with apples here, right? So you look at the smallest set on which both converge. So this still does not contradict the theorem because this didn't converge on all of R. Right, so the sum is going to converge on, I mean, it's like looking at domains, right? If you have one function on one domain, another function on the other, when you add them, you can only talk about the intersection of the domains. Richard is asking why the sum was equal to log 2, but Benjamin has answered the question right above you, right? We said that log 1 plus x to the 4 was equal to this for all values between -1 and 1. So when x is 1, you get exactly that. So when x is 1. Exactly. The sum would at least converge on the intersection, maybe for larger values. Correct. How are we doing here? Shall we move on? Right, so I think we've answered our first question that arose naturally. What are these objects, right? These are power series, and we can do right, Hugo, not radius, but interval. Interval of convergence would be at least as big as the smaller interval of convergence. Because the problem with saying radius is if they're not at the same center, then you're kind of in trouble. If they are the same center, then you're fine. All right. Let's move on. Let's move on to the second question, right, which arose naturally when we observed this thing. Right? I mean, the first question is, what is this? We defined this as a power series and studied these properties. Now, the next question that arises naturally is, are there other functions for which can we represent other functions as power series? Well, we kind of did, right? If there was a nice relationship between a function and the geometric series via differentiation, integration, and so on and so forth, works very nicely. But what about more general functions, which have absolutely nothing to do with geometric series? Maybe like sine or cosine, tangent, exponentials. What then? So given a function, f of x, can we represent it as a power series? That's the question we want to answer, right? If you're given a function, can we represent it as a power series? Well, what is this? Right, this. So given a function, can we write it? What is this? This is a0 plus a1x, a2x squared, a3x cubed, and so on and so on. So given an arbitrary function, can we write it as a power series? Can we write it as an infinite polynomial? That's the question. If so, what are these coefficients? A0, A1, A2, A3, A4. What are they? Well, observe immediately A0. If we plug in 0 This is 0, that's 0. Everything is 0 except the first term. So A0 has to be the function at 0. What about the rest? Well, let's differentiate. If you differentiate both sides, this is just a constant, so the derivative is 0. Derivative of a1x is just a1. Derivative of a2x squared is 2a2x. Derivative here, and observe that when you plug in 0 again, right? When x is 0, that's gone. That's gone. Everything is gone except for the first term again. Exactly, Tom. We're working our way into Taylor's series. So, recap. A0 has to be the function at 0. A1 is the derivative at 0. Let's keep going. Differentiate again. Second derivative. That's gone. Derivative here, 2a2. Derivative here, 3 times 2, a3x. I'm leaving it as 3 times 2 so that we see what's going on. Somebody's asking the obvious questions. How many times do we need to differentiate? Well, we're going to differentiate here as many times until we see what's happening, until we see the pattern. Because the question we want to answer is, what are these coefficients? So we found the first one. We found A0, we found A1. Let's keep going until we see what's happening. 4 times 3, a4x squared. The next one would have been 5 times 4, a 5x cubed, and so on. And again, plug in 0. So everything cancels except this first term. So we see that A2 is the second derivative over 2. Second derivative at 0 over 2. So we have the first 3 terms and keep going until we see a pattern. Third derivative. What is the third derivative? Derivative of this is just a constant. 3 times 2, a3, plus 4 times 3 times 2, a4x. Next one, 5 times 4 times 3, a 5x squared, and so on and so on. And again, plug in 0. All the terms cancel except the first one. So you see that A3 is the third derivative over 3 times 2, or 3 times 2 times 1, or, as Taha suggests, 3 factorial. Well, it's only to point out what's happening. If you see the pattern already, you're good to go. Right? What's the next one going to be? right? Just by looking at this, when you differentiate once more, I think it's easy to see that the fourth derivative at 0 is just going to be 4 times 3 times 2 times 1, a4. So a4 is going to be the fourth derivative over 4 factorial. And you see what's happening with the other ones, right? Can we generalize the result? An is the nth derivative at 0 over n factorial. This certainly works for 2 onwards, right? Because 2 factorial is 2. But when n is 1, 1 factorial is 1, so that works here as well. And when n is 0, 0 factorial is 1 as well. So this actually works for all values of n. Does everybody see what's happening here? So an is the nth derivative at 0 over n factorial. Isn't it beautiful? Thank you. Glad you appreciate that. So let's recap. What are we saying? If your function then an is the nth derivative at 0 over n factorial. No, that's exactly what we're saying. The an terms do follow a pattern. You're saying they don't, but they do. They do follow a pattern, and it's this pattern. Taha is asking, isn't it harder to represent a function through its derivative? Well, let me ask you this. Let's calculate the... So by the way, these are called Maclaurin series. Right, a power series representation for a function around 0 is called a Maclaurin series. And Taha is asking the excellent question, isn't it harder to represent a function through its derivative? And to answer that question, I'm going to suggest, think of sine x. Well, you know, you're thinking about sine x and you're thinking to yourself, I don't have an issue with sine x. I know its graph. I know how to evaluate sine. I just punch it into a calculator. But go back 100 years when we didn't have calculators. When we didn't have calculators, how would you evaluate sine of 1? Now we're in trouble. Now we're in big trouble. Big trouble. How do you evaluate sine of anything that isn't a good triangle? Well, let's discuss that. Let's work out the Maclaurin series for sine. I like to have 2 columns, functions and functions evaluated at 0, right? Because we're going to make use of this beautiful observation here. So what is the function at 0? What is sine at 0? You know that to be 0. The derivative What's the derivative of sine? Derivative of sine is cos. Derivative at 0. You know what it is. It's 1. Let's keep going. Let's keep going until we see a pattern arising. Derivative of cos. Negative sine. Derivative at 0. Sine of 0 is once again 0. Third derivative. Derivative of sine is cos, so this is negative cos. Third derivative at 0 is negative 1. Fourth derivative. Derivative of cos is negative sine, so negative negative gives us sine. And sine of 0 is again 0. And now we're going to stop. Exactly right. I'm going to stop right here because you recognize that you're back where you started. So you're going to cycle through again and again. So now you see what's happening. Now you've got the pattern. So let's put everything together. Right, we just worked out that f of x is f of 0 plus f primed of 0 over 1 factorial x. Second derivative over 2 factorial x squared, and so on. So in this case, sine x is function at 0, so that's 0, plus derivative over 1 factorial x. Second derivative at 0 over 2 factorial x squared. Third derivative at 0 over 3 factorial x cubed. And so on and so on. The next term, the next derivative, well, I mean, we're back here, so it would have been 1 over 5 factorial x to the 5, and so on and so on. Let's clean this up, getting rid of the zeros. What do we have? That's gone. We said the next one was 1 over 5 factorial x to the 5. We stopped there because we understood the process. So we should be able to write down the next few. Plus 1 over 5 factorial x to the 5. Next one would have been minus 1 over 7 factorial x to the 7. The next one would have been a plus 1 over 9 factorial x to the 9. And so on and so on. Only odd, absolutely. Absolutely, right? Because the even ones are all 0. And they cycle through. So all the even ones are going to be 0. We only have the odds. My question to you, can we represent this in a nice closed form? Can we give a nice closed sigma notation form? What do we recognize? Well, I think we have recognized Sinbad is suggesting 1 over n factorial x to the n, but I think it was observed originally that we only had the odd powers. But Sinbad does recognize the fact that it is an alternating sum, right? positive, negative, positive, negative. So we do have a negative 1 to the n, or negative 1 to the n minus 1. We don't know. We'll adjust. We only have the odd powers. X to the 1, x to the 3, x to the 5. How do we represent odd powers? And I think Nicholas has suggested x to the 2n plus 1. Absolutely. And the numerator is always 1, so that's taken care of. And the denominator, 1 factorial, 3 factorial, 5 factorial, 7 and 9, that's actually the same thing as the power. So it's the power factorial. Where do we start? We want the first one to be x, so n better be 0. And now, we had choices here. Could have been negative 1 to the n, could have been negative 1 to the n plus 1. We don't know. We wrote something down. Now let's make sure that it's correct. Let's make sure that it's correct by writing down the first few terms, making sure that we get exactly what we are expecting. When n is 0, negative 1 to 0 is 1, x over 1 factorial, so you do have an x, looking good. When x is 1, this is negative 1 to the 1, so negative x cubed over 3 factorial, exactly what you wanted, and so on and so on. When x is 2, this is negative 1 squared, which is going to be positive 1, x to the 5 over 5 factorial, and so on and so on. We're looking good. We're looking good. There it is. So what are we saying? We are saying what are we saying? We're saying that sine x is equal to this. And an excellent question. And when it's asking, what is the interval of convergence? Let's work that out. It's a natural question to ask. For what values of x is this valid? Again, be wary of the trap here, right? 2n plus 1 plus 1. Same thing with the denominator here. All right, let's clean that up. The negative 1s don't really play a role because you're in absolute value here. Here we have x to the 2n plus 3. 2n plus 3 over 2n plus 3 factorial. And we're dividing by a fraction. Let's multiply by the reciprocal. 2n plus 1 factorial over x to the 2n plus 1. The whole thing in absolute value. 2n plus 1 and 2n plus 3 factor out, leaving us with just an x squared. 2n plus 1 factorial versus 2n plus 3 factorial. You know what's happening there. This is x squared over, you tell me, over what now? Over 2n plus 2, 2n plus 3, thank you. Whose limit is? Oh, there are conflicting answers there. A lot of Benjamin had it right the first time. 2n plus 2 times 2n plus 3. Convince yourselves. Does everybody have that? Does everybody have 2n plus 2, 2n plus 3? That's the important thing here. It was a trap that you did not fall into, right? Whole limit is 0. The whole limit is 0. Conclusion? Whole limit is 0. 0 is less than 1. So the interval of convergence, this converges for all real numbers. Exactly that. The interval, it's an infinite, the radius of convergence is infinite. The interval of convergence is all real numbers. Absolutely. So now let's answer Taha's question. Originally, isn't it harder to work with this than with this? Well, it is for you. It is for you because you have a calculator. So you can work out anything you need about sine. And you are just going to plug in, if you're evaluating sine of 1, you're going to plug that into your calculator and it's going to give you a value. But how? Wait, Grisha, what's the question here? Sine is convergent. We have removed that. Very well. So, you plug that into your calculator and you're good to go. Everybody's happy. But how does the calculator know what sine of 1 is? It's all good. How does the calculator calculate sine of 1? Well, it uses the Maclaurin series. Sine is this for all values of x. So when you plug 1 in, this is what sine of 1 is. Absolutely. Calculators use exactly this. Exactly, Sinbad. We have shown that this series converges, and it converges to sine x for all values of x. So this is what calculators use, or if you go back 100 years before calculators, how would you calculate sine of 1? Well, you would use this. And now let's do it, right? Because, your calculator only has 8 digits. So as long as it spits out an answer that is correct to 8 significant digits, you're good to go. So it uses this to approximate that to 8 significant digits. And what is this? Well, this is an alternating series. This is a convergent alternating series that satisfies the hypotheses of the alternating series test. Let's verify. Limit of 1 over 2n plus 1 factorial. Well, this is easily seen to be 1 over infinity, which is 0. Now you need to show that it is decreasing. But that is simple as well, right? Because 2n plus 1 factorial is less than or equal to 2n plus 1 factorial times 2n plus 2 times 2n plus 3, because these are both bigger than 1. Correct. You're absolutely, Benjamin is absolutely correct in saying that we don't need to show that it converges. We already know it converges. You're right. What do I want to do here? Here I want to approximate sine of 1. I want to approximate sine of 1 to, let's say, 8 significant digits, as your calculator would do. So how does your calculator do that? Because, no matter how good your calculator is, it's not going to be able to add infinitely many numbers. So there's no hope of that. So really the question is, how many numbers must it add to make sure the first 8 significant digits are correct? And we can answer that using the result of the alternating series test. You know that if an alternating series satisfies the hypotheses of the alternating series test, exactly the same that we did at the end of 141. Correct. You know that if it satisfies the hypotheses of the alternating series test, then, let me finish proving that it satisfies the hypotheses of the alternating series test. So we have established, and if you multiply by 1 over 2n plus 1 factorial times 2n plus 3 factorial, we get the result we want, 2n plus 3 factorial less than or equal to 1 over 2n plus 1 factorial. And this is actually 1 over 2n plus 1 plus 1 factorial. So we've shown that it is decreasing. So it satisfies the hypotheses of the alternating series test, and consequently, as people have suggested, this is essentially where we ended with 141, in that the difference between what the series converges to, and an approximation, namely the sum of the first n terms, in absolute value is less than or equal to the next term in line. A beautiful result. Very useful in this context. So this will tell you how many terms you need to add to approximate sine 1 to any level of accuracy that you want. So if you want this less than 1 over 1,000, say, then we need 1 over 2n plus 3 to be less than 1 over 1,000. So n should be whatever. This is factorial. So now a bit of trial and error will give it to us. Right, if n is 5, no, too late. If n is 4, this is 1 over 11 factorial. This is already much less than 1 over 1,000. And if n is 3, 6, 7, 8, 9, 1 over 9 factorial. I don't know what that is. That's probably way, way less than 1 over 1,000. N is 2. 4, 5, 6, 7, 1 over 7 factorial. What is that? 1 times 2 times 3, 4, 5, 6, 7. 24, 120, 7, 20, 720 times 7. That's already less than 1 over 1,000. And if n is 1, should have started small, right? It's 1 over 5 factorial. So 20 times 6, that's 120, which is bigger than 1 over 1,000. There you go. So n is 2. In other words, if you add from 0 to 2, 1 over 2n plus 1 factorial, which is 1 minus a third, 1 minus 3 factorial, plus 1 over 5 factorial, right? So if you just add these 3 terms, you're going to get an approximation to sine 1 that is correct to within 1 over 1,000. It's actually correct to much better than that, right? It's 1 over 1,054, as Taha suggests. But there it is. It's amazing stuff, absolutely. And this is exactly how calculators calculate sine of whatever you punch in. So that's the beauty of Maclaurin series. Very, very, very useful. while it seems like it would be more difficult to work with an infinite series than with the actual function, you will need to approximate functions using the same technique, absolutely. Does it also reduce the number in range? Well, I mean, obviously, right? Well, I mean, I say obviously, it's probably faster to not reduce. Yeah, because I mean, if you're looking at sine of 3, say, it's probably much easier to plug in x equals 3 into this than anything else. I would not think that that's how Greek mathematicians approximated sine. No, this comes much, much, much later. Let's consider another important. Well, I mean, you know, you're certainly welcome to run to the fridge and get a snack or something. I mean, you'll pick up Maclaurin was born in 1698. Thank you for that information. Let's calculate the Maclaurin series for cosine x. All right, so let's redo the same thing. We'll do 2 columns, function and its derivative, and then the derivatives at 0. Cosine of 0. You know what cosine of 0 is? Cosine of 0 is 1. Derivative. Derivative of cos is negative sine. Derivative at 0. Second derivative. Derivative of negative sine is negative cos. Second derivative at 0. Third derivative. Derivative of cos is negative sine, so this becomes sine. Third derivative at 0. Fourth derivative. Again, we keep going until we see a pattern. Derivative of sine is cos. And now you see the pattern, right? We're right back where we started. Exactly. Taha has noticed that it's essentially the same thing as sine, but with the evens instead of the odds. Let's make that completely clear. And a very nice observation by student with perhaps last name Mers that suggests, could we not have just differentiated or integrated the Maclaurin series for sine? We'll discuss that momentarily. Let's work out, though, the Maclaurin series directly, since we've already done all the work. This is, in general, f of 0, f prime of 0 over 1 factorial x. Second derivative over 2 factorial x squared, and so on and so on. In our case, we're looking at cosine. So cosine x is the function at 0 plus the derivative at 0 over 1 factorial x plus the second derivative at 0 over 2 factorial x squared plus third derivative over 3 factorial x cubed, fourth derivative over 4 factorial x to the 4, and so on and so on. Let's again clean that up, getting rid of the zeros. This is 1 minus 1 over 2 factorial x squared. That's gone. 1 over 4 factorial x to the 4. The next term would have been minus 1 over 6 factorial x to the 6, and then a 1 over 8 factorial x to the 8, and so on and so on. Again, can we realize this as a nice closed form? People have suggested the answer again, right? I mean, it's an alternating series, so maybe negative 1 to the n. You notice that now it's the even powers. And how do we represent an even number? People have given it already. 2n, right? 2n is even. And the denominator is the same as the power. 2n factorial, where n starts at 0, right? We want the first term to be 1, when n is 0. Well, I mean, let's write down the first 3 terms to make sure that we have not made a mistake, right? When n is 0, negative 1 to 0 is 1. X to the 0 is 1. 0 factorial is 1. Everything is 1. Plus when n is 1, so minus x squared over 2 factorial. Looking good. Let's do one more. When n is 2, plus x to the 4 over 4 factorial, and so on and so on. Very nice. So we know that this is correct. Christina is asking, should the second term added be positive? Sorry, this should have been a plus. Right, I mean, it's plus the second derivative at 0 over 2 factorial x squared, and so on and so on. Thank you. Yeah, I mean, I had written negative here, but it's plus. It's plus the derivatives. The derivative happened to be negative here. Grisha is asking, how far off would the approximation of cosine be if we re-indexed from sine instead of doing it from scratch? What does that mean, though? How would you re-index the sine series? I'm not sure what you mean there. It's all good. It's all good. I thought maybe you had a nice observation to make that I hadn't foreseen. That would have been nice. No worries. Let's ask the question: for what values of x does this converge? What is the interval of convergence? It's all good. Nicholas is suggesting all real numbers. Let's work it out. It's a nice exercise to work it out. Very nice. How is only one term of the Maclaurin series enough to approximate to within 8 digits? It is not. It is not. It is not. It is not. What we proved, we didn't do it to 8 digits. We just did it to 1 over 1,000. And we suggested adding not just one term, but adding 3 terms was sufficient to get it to 1 over 1,000. In fact, we showed it was correct in 1 over 5,040. But probably, I mean, it doesn't prove that it's correct to 8 digits. It just proves that it's correct to an error of 1 over 5,040. Nicholas is suggesting that it should be the real numbers since it's the derivative of sine, and that's a very nice observation. We'll make that clear momentarily, but you're absolutely right. But let's just work it out. I mean, the negative ones don't make a difference here. X to the 2n will cancel. And this is 2n plus 2 factorial divided by 2n factorial, well, or rather the opposite, right? What does that leave us with when we work that out in our heads? We have an x squared on top. And what do we have in the bottom? 2n plus 1, 2n plus 2. Thank you, Benjamin. We've skipped 1 or 2 steps here. I believe you can work that out. Right, you have a 2n factorial which moves to the top, and this is a 2n plus 2 factorial. So that cancels out, leaving you with 2n plus 1, 2n plus 2 in the denominator. With a limit of 0, as Benjamin has suggested. 0 being less than 1 converges for all x. Same as for sine x, absolutely. And let's put this together and do the obvious observation. Well, I mean, it's not absolutely obvious, but it's a nice observation, right? We had the series for sine x. As this, we have the series for cosine x. Well, let me not write it, but let me say, what do I want to say? We had the series for sine x, and this converged for all real values of x. This is really a power series. So what we have here is a power series representation for sine x. And by the theorem we saw yesterday, you know you can differentiate and integrate term by term in the interval of convergence. So if you differentiate the whole thing, the derivative of sine is cos. If you differentiate term by term here, the only thing that depends on x is this. The derivative of x to the 2n plus 1 is 2n plus 1 x to the 2n. (2n plus 1 over 2n plus 1 factorial). You see that these cancel out, right? These cancel out, leaving you with just 2n factorial. Exactly the series for cosine x that we just found. Right, so you can differentiate term by term, and you know the radius of convergence is at least as large. So here the radius of convergence here was infinite. So the radius of convergence here has to be infinite. There it is. Beautiful. How are you doing? Let me point to another nice observation. What do you know about the sine function? You know the sine function is an odd function. Sine function is odd. It's made up of just odd powers. The cosine function is even. It's made up of just even powers. If you make Ranjal is suggesting if you make a change of variables, a re-indexing, n is equal to n minus 1, if you replace n with k minus 1, observe that this becomes 2 times k minus 1 plus 1, which is 2k minus 1, not just 2k. So it's not going to work. You're not going to get the cosine. You're not going to get the even powers from the odds. An excellent observation, Taha. We'll get to that momentarily. But before we do so, let us do one more. Let us do one more. Let us do the Maclaurin series for the absolutely. Nicholas is on the right track here. It's logical that the interval of convergence is all of R since sine and cosine are defined everywhere. But let me remind you that earlier today we looked at the power series for this function. And we saw that it was actually just negative 1 to 1. How does that differ? Because this is still defined for all values of x. So with that same logic, shouldn't the interval of convergence be all of r here? I'm going to let you think about that. The answer is very nice. And let's consider e to the x. We're looking for the Maclaurin series for e to the x. So we're going to do those two column things again, right? Derivatives at 0. So a function at 0 is 1. Derivative at 0 is 1. And you keep going until you see a pattern. I think Nicholas has seen the pattern. Let's do one more just to be safe. But I think it's painfully clear to everyone that the derivative is always e to the x. So Maclaurin series, f of 0. F prime is 0 over 1 factorial x. Second derivative at 0 over 2 factorial x squared, and so on. In this case, so what are we saying? E to the x is function at 0 plus derivative at 0 over 1 factorial plus second derivative at 0 over 2 factorial x squared, third derivative at 0 over 3 factorial x cubed, and so on and so on. Can we realize this as in a nice closed form? X to the n over n factorial. Let's just write down the first few just to make sure that this is correct. When n is 0, x to the 0 is 1 over 0 factorial, which is also 1. So we're starting out with 1. X over 1 factorial, x squared over 2 factorial. Looking good. Very nice. Very nice. Do we want to take a moment to work out the interval convergence? What does that simplify to? Does everybody see it? Absolute value of x over n plus 1, thank you. X in absolute values though, right? Thank you. And the limit is? Everybody don't forget your absolute values, right? Limit is, thank you, Krishna. Limit is 0. 0 is less than 1, so converges for all real numbers. Well, the n plus 1 is also an absolute value, but since we're looking at the behavior as n goes to infinity, it's always positive. So there's no need. In particular, the series 1 over n factorial from 0 to infinity converges to Nicholas. Okay, what is this? This is 1 plus 1 over 2 factorial, 1 over 3 factorial. You're adding positive numbers. It's not going to converge to 0, but rather to e. Absolutely. Thank you. Right? It's this when x is 1. Right? It's this when x is 1. We have e to the x is equal to that, and this is valid for all real numbers. So when x is 1, you have this. Similarly, this is equal to one over e. Thank you. 1 over e. Is everybody with us here? Is that clear, everyone? Very nice. Questions? So, what have we been doing? We've been taking arbitrary functions and writing them as exactly, Christina, because x is -1 in this equation here. Absolutely. We've been taking arbitrary functions and finding a power series representation for them. Let me say, a Maclaurin series is a power series representation, and vice versa. A power series representation is a Maclaurin series. Power series representations are unique. So if you have a power series representation, then you have the Maclaurin series. So you have the systematic way, right? Function at 0, derivative at 0, and so on. Right? You have this systematic way of finding a Maclaurin series, but you also have shortcuts, as we saw in the previous section, where you can use the idea of differentiating, integrating, geometric series, and so on, right? To find the Maclaurin series for cosine x, you could have just differentiated the sine series. And you didn't have to go through this whole systematic way of doing things. Let's take a few examples from the book. We are asked to find the Maclaurin series. Any way you want. If the series converges, it also means we can only look at the n first observations and have an error of 0. I'm not sure what you mean by that, Hugo. Are you saying if you have a finite series, if you're only adding finitely many terms? I'm going to let you answer that. In the meantime, let's find the Maclaurin series. So if you only have a series with n terms, that means yes. So absolutely. Then you're absolutely right. But that, what are the implications of that? A function which has only, whose Maclaurin series is finite, would necessarily have to be a polynomial. And a polynomial is its own power series or its own Maclaurin series. And there you have it. Tom is asking, by finding a relation between Maclaurin series of a function, can we assume we found a relation between the functions? By finding a relation between the Maclaurin series of a function and what? I feel you're missing. I feel I'm missing something here. You're talking about a relationship between a Maclaurin series and a function. Are you equating a function to a Maclaurin series? And then you can, so I mean, I think I understand what you mean here, and we're going to do that. Can we compose here, say x equals g equals x to the 4, and then define f of g? You can, and use the previous definition. Interesting. But you wouldn't want g to the 4. I think you would want x to the 1/4, and then yeah, okay. So I think you're going towards the fact that Maclaurin series are unique. So if you have a Maclaurin series, or if you have a power series representation, then you have the Maclaurin series. And so the answer to your question is yes. How did we use the center 0 for sine, cos, and e to the x? Well, I mean, we evaluated at 0. You're asking an excellent question. Can we generalize the result? And the answer is yes. We'll see that in a few moments. But first, let's look at this. And I think, Taha, what you want to do is exactly what we're going to do. And Benjamin had suggested a nice relationship with the question we did earlier, and I think we'll make use of that as well. And we'll see a bunch of ways. I think everything fits nicely together, but absolutely Sinbad is suggesting that we differentiate. Derivative of ln is 1 over times the derivative of the inside, which is just 1. So the derivative is this, which is, we're going to manipulate to realize it as a geometric series. And then we can just integrate term by term. And then you know that this converges for x between -1 and 1. And then we can integrate term by term in the interval of convergence. So ln x plus 1 is just the antiderivative of this. So that's -1 to the n, x to the n plus 1 over n plus 1, plus an arbitrary constant of integration. Or if we reindex, again, you might not necessarily need to, but it's a nice to do, because you get x to the n. And you know that the radius of convergence is at least as large. Somebody had suggested, it might have been Benjamin, or somebody else, that in fact the book says the radius remains the same, which it does. So you know that it's going to be valid in -1 to 1. So in particular, when x is 0, so c is 0, right? I mean, the endpoints could be included. We don't know. We haven't checked those yet, but the interval of convergence certainly includes 0. And so we get, without too much work, the fact that this is the Maclaurin series. This is valid in at least -1 to 1. Maybe we want to check the endpoints now while we're here. -1 to the n minus 1 times -1 to the n is -1 to the 2n minus 1. And 2n minus 1 is always odd. -1 to an odd number is always -1, so that's -1 over n. Which you know to be a divergent Absolutely. So -1 is not included in the interval of convergence. What about +1? And we've seen this series so many times today that there's really no point in going through a whole thing again. This is a conditionally convergent. So the interval of convergence does not include -1, but it does include 1. And Taha has suggested that if x is -1, we have an issue here. Ln of 0 is not defined, so you would not expect it to be in the interval of convergence. Very nice. Very nice. Can you put that together with the question maybe Benjamin was asking earlier? I forget if it was Benjamin or somebody else, about the ln of 1 plus x to the 4. Do we see what's happening? Somebody was talking about interval of convergence for sine and cosine, saying sine and cosine were defined everywhere, so we were good. We expected the interval of convergence to be all real numbers, but now that argument failed right here. So Nicholas, right? Very good, Nicholas, thank you. Nicholas, did you work that out? Did you see? I think it's going to be easier to see with the square. I think it's easier to see with the square. I claim the interval of convergence here will still be -1 to 1. Your thoughts on that? It's not obvious. It's not an obvious answer. Let me suggest that the term radius might play a role. Radius of convergence. Right, but why doesn't it work outside? Why stop at 1? Even though this is defined everywhere. Much like sine x, cosine x are. Well, I mean, it has to do with what Taha was suggesting, that, in the previous example, ln of 0 didn't make sense here. So ln of 0 is going to be an issue here. But for what value of x? When is this 0? Well, you're right. People are saying it's never zero. It's never zero in the real numbers. As Wing has suggested, at I, or the square root of -1, then you're in trouble. So this idea of Taylor series or Maclaurin series extends to complex numbers. And in the complex plane, in the real versus the imaginary, you have issues at I and -I. And that's where the whole idea of radius of convergence plays a role. Because, here, radius of convergence is 1. I defined it to be half of the interval of convergence. But you know what a radius is. It has to do with a circle. And that's what happens. That's what happens when you move to the complex plane. You get circles. And you have convergence everywhere in here until you hit a problem. So in the ln of 1 plus x, Taha suggested you hit a problem when x is -1. So that restricts your interval. And that's what happens. You have a problem when you hit -1, so it restricts the radius of the circle. Here, you don't have an issue with real values of x, but you do have issues with imaginary complex numbers. When x is plus or minus square root of 1, or when x is plus or minus I, it stops the circle, stops the disk. So that's what happens. Of course, we're not considering this, but everything extends to the complex numbers. Correct. We're not discussing complex numbers, but I'm just pointing out that this whole idea of Taylor and Maclaurin series, extends to complex numbers. And there you get the full feel of, first of all, the word radius, because you're dealing with disks, not intervals. And you can predict how large your disk of convergence is going to be. Well, the interval of convergence is still -1 to 1, and that's because that's because you have problems at plus or minus I. So you can actually predict or how large your interval of convergence is going to be. It does. Christina, it really does. The complex numbers affect the interval, even though you're restricting your attention to R. So if you have knowledge about the complex numbers, you're going to be able to predict how large your interval is going to be. That's a very nice observation here. But again, we're not considering that. And when it's suggesting that Maclaurin series have to be in the form of derivative factorial, how was the last example Maclaurin? Well, a Maclaurin series is a power series. So if you have a power series representation, then you have the Maclaurin series. We did it using a shortcut. You can do it the long way, and I'm going to invite you to do that. Do we want to get started? Let's let's get started. We had this, and we saw. Let's quickly redo the last example. We had this, and we worked it out to be, I think we worked it out to be this. Is that correct? Nicholas, an excellent question. Let's do this. I'm going to let you think about it. Going to let you think about that for a moment. And I'll answer that question in a moment. We worked out, so anyone is asking, here we don't have factorials or anything. How is this a Maclaurin series? You know, we worked it out in a nice shortcut, but we can work it out in a long systematic way. And let's do it just to convince ourselves that we have the same answer. F of 0 is, of course, ln of 1, which is 0. Derivative of ln 1 over 1 plus x times the derivative of the inside, chain rule, right? Derivative at 0 is 1. Second derivative, this is 1 plus x to the negative 1. So negative 1 plus x to the negative 2 times the derivative of the inside. Second derivative at 0 is negative 1. Third derivative, 2, 1 plus x to the negative 3. Third derivative at 0 is going to be 2. Let's do one more. Minus 2 times 3. 1 plus x to the negative 4. I'm not writing it as negative 6, only to see what happens. Fourth derivative at 0, minus 2 times 3. So now if you use your full formula, what do we get? 0. So this was ln of 1 plus x. Derivative over 1 factorial x. Second derivative over 2 factorial x squared. Third derivative over 3 factorial x cubed. Fourth derivative over 4 factorial x to the 4. The next term would have been 2 times 3 times 4 over 5 factorial x to the 5, and so on and so on. And you see, exactly as Taha says, it cancels the factorials. It cancels the factorials. What do we have? 1 over 1 factorial x, or 1 over 1, or just x. Minus 1 over 2x squared. And the 2 over 3 factorial is really just 1 over 3. And the 2 times 3 over 4 factorial is really 1 over 4. So you see that this is just x to the n over n with a negative 1 to the n minus 1 or n plus 1. Exactly what we had. Well, if the question is asking you to find a Maclaurin series, you have, in some cases, you have options. any way is possible, right? If you take the derivative, you notice that this is essentially a geometric series, and you can use that shortcut and then integrate term by term and get your answer. Everybody's happy. If you don't see it and you do the long way, works just as well. Nicholas, did you find the answer? Where's the issue? Where's the issue? The issue is if 1 plus x to the 4 is equal to 0, or x to the 4 is equal to -1. If you take the square root of both sides, if x squared is plus or minus the square root of 1, or of -1, or plus or minus I, so let's just concentrate on one of them. It doesn't have, exactly, it's the fourth root of -1. Fourth root of -1, or square root of I. And you can work out what that has to be. What does it have to be? I want to say 1 over root 2 plus I over root 2. Is that correct? When you square them, you get this squared, this times 2, plus this squared, and I squared, since I is the square root of -1, I squared is -1, so this is just I. There it is. Sure, absolutely, but it's also this, right? So if x is 1 over root 2 plus I over root 2, then we're in trouble. And in the complex plane, this is right here, right, where this makes a 45-degree angle, pi over 4, and it's on the circle of radius 1. So that's why it stops it at -1 to 1. No, it's not I squared squared. It's square root of I. Right, I'm saying x is the square root of I, which I have conveniently rewritten as this. One or two more examples and we'll call it a day. I'll open, well, first of all, what works zeros already opened up. Of course, it's not for marks. I assume everybody's familiar, but I think at least one person wanted to see it, so it's there. I will open up a new web work today. We're not 100% finished with all the material, I suspect, but I'll open it up right after class. It's called assignment 2. Don't be alarmed. There is no assignment 1. It's called assignment 2. That's it. Yeah. I did not have time to look at the results of the poll. So I'll give you another day to vote. But today, I mean, I'll first thing tomorrow morning, I'll announce, well, I mean, in class. We'll go with whatever you guys decided. Last time I checked, I sent an email. Did people not get the email? Did everybody get an email? It is under, in the content section, there's just go to the content section on my courses. But I sent an email yesterday. Nobody got the email. Jeez. It sent an email to me. I figured everybody had the email. Oh, wait, 2 people got an email? All right, I don't know what's happening. Okay. Well, maybe look at your spam folder. Everybody should have gotten an email. But no harm done because it's just a survey. So please go ahead and fill out the survey. No. I use the my courses 222 class list. Okay, I'm going to look into why you didn't receive one, but please go ahead and fill out the survey. Regardless, I'll give you another day. But tomorrow we'll announce the date of the midterm. Last time I checked, people were voting for Monday. Monday was in the lead. We're looking for Maclaurin series for this function. Okay, that's it's questionable. I don't know what happened, but some people got it, some people did not. I received it immediately, so I figured everybody had it. All right, let's not worry about it. Everybody now knows. We will, I mean, we have class every day that we're supposed to have class. So regardless of whether we have the midterm or not, it's in the spam. All right. We're looking for Maclaurin series for this function, but you know already, we have just seen that the sine series, I mean, there's no point in redoing it again. And when I say again, I mean right now in this course, because we just did it half an hour ago. There's really only just the one day that's a class day. It is Monday. People seem to want it on a Monday. Not sure why, but frankly, I would have taken the weekend. Right? I mean, we know this, and we know that it's valid for all x. So now replace x with 3x. right? What's happening here? We're doing a composition. It's a composition of power series. Right? This is a polynomial. This is its own power series. And now we're just doing a composition of sine x and 3x. This, being a polynomial, finite, converges for all values of x. This converges for all values of x. So the composition is going to converge for the minimum of the two, at least for the minimum of the two. Well, I mean, it worked for both reasons, right? You're composing one power series, which has an infinite interval of convergence, with another power series, which has an infinite interval of convergence. So the minimum, so these are going to converge for all values of our minimum of the two radii of convergence, since they're both around zero, since they're both centered at zero. Is exactly the minimum of 3x and sine x, precisely. Or the intersection. So let's clean that up. -1 to the n, 3 to the n, 3 to the 2n plus 1, x to the 2n plus 1, over 2n plus 1 factorial. When can't you compose? You can always compose. You can always. Here, we made this argument so that we didn't need to work out the interval convergence. I'm suggesting that the interval convergence is all of R. And we see 3x as a power series here. Exactly. Right? I mean, since this converges for all of R, and this converges for all of R, their composition is going to converge for all of R. If you don't want to use that result, simply find the interval of convergence. You'll see that it's all of R. Exactly that, Charles, yes. Last line on the right, thank you. Thank you, absolutely. So there it is, this is sine of 3x. And it converges for all real values. All right, I think we've had enough for the day. Thank you all for coming. I'm going to open up web work. It'll probably include a lot of series, just as a nice refresher. When will office hours start? I'll have office hours right after class. So if you want to see me, I'll open up a Zoom meeting, and so I'll have office hours for probably an hour after class. I'll post them on my courses immediately. Well, I mean, give me 10 minutes. Very good. So if you need to see me, I'll be available today. And otherwise, I'll see you tomorrow morning, and we'll set a time for the midterm. Thank you all for coming, folks. See you soon.